Okay, hopefully you all were able to watch the intro video. So this will be the video voiceover for Chapter 1 for Earth System History. I want to start off by saying I will eventually have a little video down here of me as I'm talking to make this seem less foreign, but my camera isn't here yet, so expect that within the next couple lectures to show up. Okay, so Earth System History. In this class, we will study the physiochemical and biological changes that have occurred on our planet since its formation 4.56 billion years ago. Some of the guiding questions we're going to use is kind of what fundamental principles guide geologists as they reconstruct Earth's history. Many of these principles can be broken down to something I call first principles. Well, not just me, most of the scientific community calls them first principles. And by that, I mean the principles of thermodynamics and physics. For example, if you see the neighborhood kids playing baseball when you leave for work, and you come home to a baseball in your living room in a broken window, there are some basic ideas you can come up with for how that got there. You most likely wouldn't think that a tiger escaped from the zoo, stole the baseball from the kids, and then threw it through your window. You would more probably imagine that they accidentally, or on purpose if you're mean to the kids, hit or threw the ball through your window. This latter example would be the simplest explanation, and that is something we call Occam's razor. The simplest explanation is most usually correct, unless you have extraordinary evidence to proving otherwise. In kind of the more plain terms, saying of Occam's razor is keep it simple, stupid. Kind of how do we unravel the age relations of rocks, and how does the lithosphere, that's like Earth's outer layers, how does that relate to the inner regions, and how does it move into form? And through the course of this history, or through the course of this class, we will look at Earth's history and the history recorded in rocks and try to make some interpretations about how our planet actually functions and how it has functioned over time. So, Earth is a library. It's a geologic record of all of Earth's past. These records form from the interaction of complex systems within the planet. Some of the foundations of geology we will start with in this course is the principles of uniformitarianism. This is also known as the present is the key to the past. There are some basic laws of nature. Think of, like, again, the laws of chemistry and physics, which we have no reason to think were different in the past. So some kind of constant uniform process probably controls the current landscape that we see around us. Actualism. This is this kind of describes that things we see being formed today by natural processes were probably formed by the same natural processes in the past. If we see some, sand ripples on a beach being formed today, and we find sand ripples of the same kind in the rock record, then we can assume there may have been a similar beach environment that formed those. And then there's this other one called catastrophism. This is the idea that things form all at once in catastrophic events. It's most likely, it's mostly untrue. This is like, biblical floods, stuff like that. And we don't see many of these catastrophes through natural history, although there are some examples of this, like the glacial Lake Missoula floods and things like that, but they're pretty rare. Oh my God, cut the sneeze. Okay. Okay. So, again, actualism. These are modern ripples on the left and some ancient ripples on the right. They look pretty similar, so they probably formed in similar environments. Okay, so some minerals and processes to think about. So a mineral is a naturally occurring inorganic solid element or compound with a particular chemical composition or range of compositions and a characteristic internal structure. Minerals are the building blocks of rocks. They have a strict definition. We'll get even more into it next lecture. But think of like ingredients in baking. If we combine different ingredients in different ways, we can make different types of baked goods. Similarly, if we combine different minerals in different types of ways and with different chemistries, then we can make different types of rocks. And so, therefore, a rock is made up of interlocking or bonded grains of matter, typically composed of multiple minerals. If we then go one step further, an outcrop or an exposure is a rocky surface that stands out and is exposed from within the soil, so that way we can actually look at it. These are especially impressive in quarries and road cuts you might see when you're driving. And you'll see geologists often flock to outcrops. You may have even seen white vans on the roadway with people standing staring at the walls, and you probably thought, wow, what a bunch of weirdos. Well, after this class, you will likely see rocks in a much different way, and you will be in danger of becoming one of us. Weirdos. So the rock cycle, this is, don't get too freaked out about it. I'm just kind of introducing it here. Just know that any rock we learn about can be modified through natural processes to eventually turn into any other rock that we learn about. And that's pretty impressive, and the Earth can do that. And it does take a long time, but it is possible. So the three basic rocks are igneous, sedimentary, and metamorphic. And we'll start with igneous because igneous are the best type of rock, and for many reasons. None more obvious than they start as a molten liquid, magma or lava. I mean, you can't argue that's the coolest. As they slowly cool down from their molten state, though, they start to solidify. And it's kind of similar to if you put water in your freezer, eventually that's going to turn to ice. Well, if you take any liquid and cool it down enough, it will turn into a solid. In this case, the liquid state is above 700 degrees Celsius, which is super hot. But as you cool it down, minerals form, and you start to solidify this into a rock. There's two different main types of igneous rocks, and those are extrusive and intrusive. Extrusive igneous rocks form on the Earth's surface. Think of like a volcano or a lava flow. And intrusive rocks form inside the Earth, like inside of mountain ranges. And so you can just think like if lava wasn't erupted from a volcano and it cooled inside the magma chamber, then it would be an intrusive rock. In these images here, you can see two igneous rocks. They're called granite and rhyolite. Granite here on the left and rhyolite here on the right. And they're essentially the same chemistry, but they have vastly different histories of cooling, so their textures look way different. But they both kind of have an overall pinkish appearance. That's from abundant levels of potassium. And the rate of cooling really affects the kind of textures we see within igneous rocks. And we'll learn more about that in a future lecture. So sedimentary rocks are next on the list, and these rocks are deposited on the Earth's surface by fluids, gravity, or ice. To make a sedimentary rock, you first need sediment, which is derived from weathering. Weathering describes the breakdown of rock at the Earth's surface. So you weather a rock to make sediment, and then once you remove that sediment through a process of erosion, that's the actual process of removing sediment, that material is now kind of in the sedimentary rock cycle. And if that material is then redeposited later on, it turns into a sediment, and over time it can kind of be glued together through some natural processes, and we call that lithification. And it only did that because it was broken down, transported, redeposited, settled out, and lithified, right? So there's a lot of steps to making a sedimentary rock, but you can break down and turn any rock into sediment and then redeposit it. So sedimentary rock is part of that cycle. So if you started off with an igneous rock and then you eroded it, weathered it and eroded it, and then those little eroded pieces got redeposited and glued together and lithified, then that would be a sedimentary rock derived from an igneous rock, right? There are many types of sedimentary rocks, all of which tell you unique stories about the origin and path of travel. Some examples are sandstone and shale, which form as physical material derived from pre-existing rocks. There's also some rocks that are formed of skeletal debris, like from shelled animals, think like clams in the ocean. These can come together to form limestones. And then there's also some chemicals that get dissolved in water. And if you trap that water into a basin and evaporate it, those chemicals become super concentrated via evaporation. And then eventually they become so concentrated that they want to precipitate to form a solid, and we call those evaporites. Sedimentary rocks form tabular layers because they're deposited via gravity. Okay, so you can think they're deposited, they're kind of flat line when they're first deposited. And that flat tabular layer of sediment is called a stratum, and it's accumulated in discrete episodes. Stratums are composed of beds. Beds are anything bigger than 1 centimeter thick, all considered to be of the same kind of discrete episode, whether that's a flooding event or river runoff or anything you can basically think of, a landslide. There's a lot of ways you can get sediments. And inside those beds, there's even more small layers called laminae, and those are less than 1 centimeter, and those can actually represent changes within a single discrete episode. Or they can be multiple discrete episodes. If you take sediment or an igneous rock and subject it to very high pressures and temperatures, such as if you bury it, really deep though, we're talking tens of kilometers deep, 5s to tens of kilometers deep, you can form a metamorphic rock. Basically what you do is you heat it up and subject it to enough pressure to where all the elements inside that rock start to migrate, move around, and form a new rock. And usually these are kind of like stratified and wavy looking, just like you see here in this picture. And that's because of different stress kind of, if you think about if you take 4 pieces of square Play-Doh or cubed Play-Doh and put them on top of each other and then flatten them, they're going to look different afterwards. So that's kind of what's going on with metamorphic rocks. Okay. Just like all the other things in science, we have a really particular way we like to name things in geology. And when it comes to rocks, we have a hierarchy, as described here on this slide, for naming rock units. And it goes something like this. A formation is a particular type of rock believed to have formed in the same particular way, such as like sandstone all being deposited at a beach. Okay, that would if that became lithified, we could call that a sandstone, and it would be given a formation name. These formations are capitalized and often are named for nearby geographic features. So one example is the Kebab limestone in the Grand Canyon. The word kebab is derived from the Paiute term meaning mountain lying down. So, and which is kind of their name for the Grand Canyon. So really Kebab limestone translates to Grand Canyon limestone. And so that's kind of how formations work. And so a member is a subunit within a formation, and this is usually designated by a change in chemistry or texture within the rock, but still is thought to have formed in the same way as the rest of the formation. And then a group is a suite of formations, okay, and all of which are thought to have been deposited one after another in a similar environment, but they might have slightly different chemistries and origins of formation. Okay, so like a sandstone's at the beach, but a limestone's deposited out in the water. And it's going to be 2 different rock types, but they could all be part of the same group if they were deposited on one on top of another in the same area. Okay, so this kind of brings us into, so now we're talking about sedimentary rocks and stuff. So this kind of brings us into Steno's principles. And there's 3 main principles here that allow you to kind of dictate what happened. That's kind of what a lot of this, Earth system history class is about. Classically, this was called historical geology, trying to figure out what the, history of the geology was. And these principles, outlined here on this slide, the first of which is superposition, will allow us to kind of tease apart these stories and try to figure out what exactly happened in certain locations. So the principle of superposition states that the oldest things are on bottom unless something happened. Okay, so just like here, time one, time two, right? You deposit one thing, and then directly on top of it, you deposit the next, and then the next, and the next. And if you went out into the field and saw those things deposited on top of each other, you could assume that the thing on the bottom was the oldest and the thing on the top was the youngest. Unless something has happened during mountain building events and things like that, things can get flipped over, and we call those overturned beds. But if you don't have any evidence for overturning, then you can assume most things are flatline. And you should probably assume most things are flatline for this course. Then that brings us into the principle of original horizontality. This is that all stratum or all beds are deposited on as horizontal when they form. So that's kind of like here, and this is kind of B time one. But if something happens, if you get some uplift underneath, or if you get some compressional forces from the sides, you can cause folding. And so if you see sedimentary rocks that are no longer flatline, you can assume something happened. And that's, again, letting us kind of figure out something about the historical geology. And lastly here, we have the original lateral continuity. So generally speaking, rock units are continuous, although there's some exceptions. But generally, if you see the same rock unit outcropping on each side of a valley like we have here, you can assume at one point that those units were all one unit, and it's just now been cross-cut by this river, and all that material has been eroded away. So why is this important? Well, actually, real quick, I want to talk about two more of kind of some cross-cutting relationships. And this is the principle of intrusive relationships. Intrusive rocks, which are younger, will disrupt or cross-cut other rock units like we see here. All right, so intrusive rocks, again, this goes back to that rock type igneous, right? So we have our intrusive and extrusive. Well, for a volcano to erupt, it needs to be fed by an intrusion. And these intrusions will cross-cut strata like you see here in this image. So what you can assume, though, is that all these strata that are being cross-cut were there first, and then the intrusion happened next. Okay. Similarly, if you are in one of these sedimentary layers, if you find bits and pieces of an igneous rock, it probably didn't come from this unit. It probably came from a previous igneous unit that is no longer there. Okay. And this metamorphic rock here is kind of ignore that. This is a contact metamorphism. Basically, if you heat up a rock, it'll change its chemistry a little bit, but it's not a lot, and we don't need to worry too much about that right now. And similarly, faults will also disrupt continuity. So I have here a cross section. So just think these are all cross sections, right? These flat panels on the front, and these are three-dimensional slices. But if we just think about the front of one of those slices, I'm gonna have you pause the video for a second and try to figure out which order things happened using the principles you just learned about. Okay, so I labeled the first one for you. Okay, C is labeled, and then now I want you to kind of try to figure out what happened after that. So go ahead and pause the video, take a couple minutes, maybe write down, C happened, and then this happened, and then that happened. Okay, so go ahead and do that, and I'll give you a few seconds, and then I'll resume talking. Okay, so hopefully you paused it. So C happened first, and then again using the principle of superposition, the oldest things are on bottom and the younger things are on top, then we should say that then B happened, B was deposited. Again, off of superposition, we should say A was deposited. And then next we got to start thinking about, okay, well, what happened after A? We have a bunch of things going here. We have an igneous rock cross-cutting this D. We have this fault here, okay, but the fault cross-cuts D, so that means D had to come before the fault because D is cut by the fault. If D wasn't there when this fault occurred, then there's no way to have cut it, right? So it looks like then D was actually intruded all these sedimentary rocks. And then what happened? Then we have the fault. So then it's E, which is the fault. And then what about a sixth thing? What happens after the fault? Because we don't have the same thickness of layers on each side, right? So A is much thicker on this side than this side. So what happened to all that extra A? and what happened to all these things above it, and what happened to the rest of the intrusion. How to get eroded. So number 6 is erosion. So then there's some erosion kind of formed the modern day landscape. And these can get a little more complicated. Just to tell you, K is an intrusion and E is a fault, so just so you know. And I will tell you that J is an erosional surface. That's what this wavy line means. So I'll give you that. And I want you to go ahead and pause it and try this one too. This one's a little more complicated. Go ahead and pause it for a few seconds and write down the order of what things happen. And I'll give you a second and then I'll start resuming talking. Okay, so hopefully you pause the video and try to figure this out. There will be things like this kind of on your, I think your first quiz will have a couple of these, or it's your second, one of your quizzes has some of these, so just try to make sure you know how to do these. So for this one, this is the order I came up with, and please let me know if I'm wrong, but I think I'm right. So I have that I, H, G, and F were deposited using the law of superposition, I being the oldest and F being the youngest in that suite. I then have they were faulted by E. Okay, so I then have they were offset by this fault E. They were then all tilted. This whole package was kind of tilted from original horizontal to a tilted position. And then I have the erosional surface J forming to erode away all those units, including the fault. See how the fault truncates against J? So that means that J, that erosional surface, had to get rid of the fault as well. I then have that D, B, and A were deposited. And then I have the whole suite, including the fault, everything being cross-cut by K. And then the river valley forming and C being deposited. Now, K actually could have intruded even after the river valley formed. There's no way to tell for sure between the two. So if you had K after the river and C, that's fine as well. Okay. So that's kind of cross-cutting relationships for you. All right, so fossils are going to be a big part of historical geology, or Earth system history, I should say, sorry. Fossils are remnants of ancient life, and they range from hundreds to hundreds of millions of years old. I like to call them rock bugs because it makes paleontologists angry, but you should probably learn their actual names for this course. Fossils are mainly important because it allows us to see how life has changed over the course of Earth's history, but also fossils capture life forms that only existed for a very short period of time. But if those very short existences were widespread all over the world, these fossils can be used as index fossils. And index fossils allow us to know a relative time of when the rock that contains that index fossil was deposited. So if we know, so if there's a layer of rocks, we'll call them 1, 2, and 3, 3 being on the bottom, 1 being on the top, and we know the ages of 1 and 3, and we find index fossil in number 2, then that we know that it has to be between the ages of 1 and 3. Well, if we then go across the planet and find that same index fossil in a rock, then we know the relative age of that rock, right? And we don't even need to know any absolute ages. So index fossils are pretty important. This also allows us to see kind of like evolution stuff, which I'll talk about in a second. Okay, so this kind of brings about the geologic timescale. The geologic timescale divides the Earth into kind of distinct ranges of time based on events that were occurring on the planet at that time. It was developed using biostratigraphy and radioisotope dating, which we'll talk about again a little later. This is just an intro. It started off really simple, but now we've done so much work in our instruments for dating have become so sensitive, we're able to resolve quite some detail. It essentially is divided, you can think of it being divided into Phanerozoic and Precambrian, which is Precambrian is before life, before fossils, and Phanerozoic is after life, after fossils. So Cambrian rocks just after the Cambrian, right? So Cambrian rocks are the oldest rocks with conspicuous fossils. And you can see here's that cutoff on a really simple geologic timescale. Here's Cambrian 541 million years ago, and that's when life kind of really started to take off on the planet. Now, I'm going to show you a more complex one, and don't lose your mind. I just want to show you how much detail we actually know now. Again, we don't actually know a lot prior to the Cambrian. When that Cambrian kicks off at 541, that's when we really start to get our ages down, because we have so many fossils. We can actually really start to pick apart the rocks. And there's just more rocks too. Onward. So Earth is kind of complexly layered, but on a macro scale, so we really zoom out, we can split it based on chemistry into a crust, a mantle, and a core. And we can split it physically on a lithosphere, asthenosphere, outer core, and inner core. The lithosphere behaving brittly, that's where you kind of get all your faulty and stuff. The asthenosphere behaving ductily, where you get kind of these things called convection currents, which we'll talk about in a second. So they're very plastic, kind of like Play-Doh. It deforms and you can't really undeform it. And the outer core is a liquid of molten iron and nickel, and the inner core is solid iron and nickel. And this is kind of where we get our magnetic field from, is that the outer core spinning around the inner core. That creates our magnetic field. So if we started as all liquid, maybe at the beginning of the planet, did we even have a magnetic field? There was no spinning of liquid around, so there's things you can think about. Has our magnetic field gotten stronger over time? Was there even any spinning to begin with? So yeah, those are all kind of questions you can ask yourself. But this solid iron inner core has gotten bigger and bigger probably throughout Earth's history as the planet has cooled. The two main types of crust are oceanic crust and continental crust. Oceanic crust is more dense and it's thinner. It's also made of mafic rocks, which leads to the density. We'll learn about mafic and felsic when we talk more about igneous rocks. But just know that it's thinner and more dense. And continental crust is thicker and more buoyant, and it's made of felsic rocks, which we'll learn more about. But when oceanic crust is juxtaposed to the thicker, more buoyant continental crust, you form large basins, which are where our oceans reside. And so that's where the respective kind of names of the two crust types were derived, right? You have your oceanic crust as oceans sit on top of them, and your continental crust is the continents that we live on. And so this can all kind of be explained by plate tectonics, and this is known as the unifying theory of geology. The lithosphere, again, that's that brittle upper portion, is divided into discrete plates which kind of move and slide past and under and over each other at plate boundaries. And these plate boundaries are considered what we call active boundaries. And this is where new crust is formed, or at spreading centers like in the mid-Atlantic Ocean, or is destroyed at like trenches, kind of like Japan or something like that. And boundaries where plates meet are considered active, and it's where we see a vast majority of the currents of earthquakes and volcanoes. The movement of plates is driven by convection. Convection is heat. It's heat inside the Earth left over from formation, and it's heat from radioactive decay of elements. And this heat is constantly trying to escape to obtain equilibrium with the colder, vast vacuum of space. This leads to large convection cells within the mantle, which, remember, deforms in a really ductile nature, right? It's like Play-Doh. So think of like really superheated Play-Doh under high pressure, kind of spinning around in convection currents. It's more complicated than that, but it's fun to think about. And as this moves, remember that the lithosphere, that brittle upper portion, actually is is crust plus the upper few kilometers of mantle. So because the brittle lithosphere is coupled to the ductile mantle, when these convection currents spin in the mantle, the crust actually moves around with it. So the two things are coupled. It's kind of like a conveyor belt. And because the mantle is coupled, these convection cells cause the crust to move around, which leads to development of plates. And where two convection cells move in opposing directions, you can then get certain types of plate boundaries. You can have, if the two are moving opposite of each other, you get your divergence. If they're moving towards each other, you get your convergence. And if they're moving kind of like laterally next to each other, you get something called transform. And that's kind of, big transform faults, kind of like this San Andreas. It would be an example of where these two convection cells are kind of moving in opposite directions, or there's some kind of weird geometry going on. So it's pretty hard to take thin flat plates on a three-dimensional surface and slide them past each other. And there's a whole science around that called geodynamics. And if you want to learn about how the plates move, you can go to grad school and study, geodynamics. And it's a lot of physics. It's a lot of physics and math, but it is fun, and they're cool problems to think about. Just not for me. I like volcanoes. Okay. So this convection, again, the two main plate boundary types, as I outlined here, you have the divergence and the convergence. That leads to spreading zones and subduction zones. Spreading zones are where plates move apart, and this happens at mid-ocean ridges and continental rifts. Mid-ocean ridge like the mid-Atlantic, or a continental rift like the East African rift. And when these move apart, there's a phenomenon that occurs that's called decompression melting, okay? So essentially, if you take a rock that's solid at one temperature, at a high temperature, under a lot of pressure, and you release the pressure, then all of a sudden those molecules in that rock can vibrate a little bit more because they're not being held in by pressure. And if you vibrate enough, it can go through the transition from a solid state to a liquid state. So that's kind of what decompression melting is. And that occurs here at these mid-Atlantic ridges, and that also occurs at rift zones. So the other boundary where you have the two plates coming together will normally form a subduction zone as long as it's a oceanic plate meeting an oceanic plate, or an oceanic plate meeting a continental plate. If two continental plates meet each other, then you get something called continent convergence, and you get big mountain building events, kind of like the Himalayas. But generally speaking, subduction zones form, and these are associated with trenches, or these form trenches, this causes a phenomenon called flux melting. And flux melting is where water is driven off of this subducted slab and pushed into the overlying mantle. And the water is a flux. It lowers the melting temperature. So basically you take something that has a really high melting temperature and all of a sudden lower it, but the temperature has stayed the same, so it melts. And then when it melts, it becomes more buoyant and starts to move upwards to form volcanoes. And so that phenomenon of flux melting happens at these subduction zones. There's also associated with subduction zones are lots of earthquakes and volcanoes. So think of Japan. It's a really good example of a subduction zone. Okay, so speaking of water on the planet, on the surface of the planet, is abundant. It has a high heat capacity, which makes it important, especially when we're thinking about issues like climate change. Most water on Earth is held in our oceans, and another vast majority is held in ice or as groundwater. A very, very minute portion of fresh water occurs in lakes and rivers, which is why the water cycle is important for providing a constant supply of fresh water. We can think of water as a dynamic, constantly changing source, and it's able to kind of transition and transport between all sorts of different systems. You have evaporation in the ocean, which can then precipitate back into the ocean. It can precipitate somewhere over the land as liquid water. It can precipitate in the mountains as ice, or what we call snow. That precipitation can turn into glaciers, or it can just melt and turn to runoff into a river. It can get absorbed into the ground and form groundwater. So there's tons of different things that water can do, and it's very dynamic in how it behaves. And there's a course called Water in the Earth that Dr. Jeffrey Vavort teaches, and it's really good, and I would recommend it if you have a chance. Okay. So we're starting to kind of wrap up this introduction here, but I want to talk about a few things, and one's directional changes. So over time, there are one-directional changes that occurred on the planet, and they're most likely irreversible. One of these is evolution. That's the fact that life has become increasingly more complex, and the other is cooling. The interior of the planet, the mantle and the core, have slowly cooled over time and will continue to do so. And so that will constantly change kind of the rate and what type of geologic activity we have. Okay, another thing I need to mention is unconformities. Because rocks on the planet are a record of time, If we have rocks that have been eroded or never deposited, okay, so if they've been removed or just were never deposited in the first place, then we call that an unconformity. And this unconformity is missing time in the rock record, okay? So if we're missing time, then we're going to have a hard time figuring out what happened. And so here's an example where you can see these kind of vertically dipping beds, maybe even lamini. And so they were deposited flat to begin with. So they're vertically dipping here, and they're eroded away. So that's obviously going to be some missing time. And there's more kind of angular dipping beds on top of them. So you had these deposited horizontally, tilted vertically, eroded away, and then you had a whole nother thing deposited and then tilted. Obviously this would have been tilted with it too, but you know what I'm saying? So this is like a very complex situation where we have a lot of missing time. And so there's three main types of unconformities. You have an angular unconformity. It's angled and it's presumed to be originally horizontal down here. And then there's some erosional surface with flat-lying sediment on top of it. And this implies that there's been tilting and erosion that occurred between the two, and this requires lots of time to occur. So that time is not recorded in any rock unit at that location. Here we have a disconformity. It's two of the same type of rocks that are both horizontal and flat-lying, but there is either a lack of deposition or erosion between the two. These disconformities are actually a lot harder to recognize in the field, but to remember it, just think disconformity is discontinuous. Okay, so you have some kind of discontinuous process here. There's not a continuous record of time. And then you have a nonconformity, which is probably the easiest to recognize and easiest to remember. And when you have this is where you have an erosional surface on top of metamorphic or igneous rock with sedimentary rock on top of it. And so you can think there was an igneous rock, it got eroded, and then sediment was deposited on top. And you can think nonconformity, not the same, right? Nonconformity, not the same. And the last little kind of bit to end the lecture for today is I want to talk about evolution. And so evolution is the slow process by which life becomes more and more complex. Small genetic mutations which are favorable for survival or reproduction over time become more prominent and are favored based on a variety of environmental stresses. Mass extinctions can lead to large changes. If the dinosaurs didn't go extinct, it's quite possible that mammalian life may have never got a strong foothold due to being constantly predated on, and we may not even exist today. We're currently living through a mass extinction. It's called the Holocene extinction, or it's also referred to as the sixth mass extinction. We're currently losing, and kind of depending on where you look on Earth, we're losing species at a rate of 100 to 10,000 times faster than the normal background extinction rate that we've seen through geologic time. The last mass extinction, we lost the dinosaurs and it led to us. So kind of what will the current mass extinction lead to? And that's just something to leave you with to think about. All right, thanks. And the next lecture you will see is for chapter 2. And as always, if you have any questions, please contact me via Blackboard or email. And I appreciate it. Have a good day.